Welcome back to CAT23. Our final speaker of the day is Grant, VE3XTV, who now lives near Toronto in Canada, but was originally from New Zealand as ZL1WTT. There, his local ATV repeater was ZL1BQ, which gave him the opportunity of making his own equipment for bands from 70 centimetres to 3 centimetres. He moved to Canada in 2016 and has built lots of DATV equipment for television. For 23, 13 and 3 centimetre bands, but now comes full circle as he experiments with narrow bandwidth television. But instead of using the original mechanical scanning with Nipkoff discs, he wants to see what can be achieved with just a few kilohertz bandwidth using modern circuitry and processing. We're in for a fascinating talk to end our convention, and don't forget you can ask Grant questions or make comments at any time using BATC messaging or YouTube chat. So a welcome to Grant in Canada. Hello, Grant.
Hello. Good morning or good evening your way.
It's sort of neither really. It's afternoon. But,
afternoon. Good afternoon.
It's quite early morning for you, I believe. Thank you very much for joining us. Yes.
Okay, well, I should get straight into it. That's a very good introduction. Yeah, I've always been involved with ATV, getting involved back in the early 1990s. I saw the ZL1BQ ATV repeater. And I saw the guys doing their thing on it, and that looked quite exciting. And being a bit of a hobbyist in electronic circuit design was my thing, I decided to get involved. And subsequently, as time has moved on, I've built more and more different circuits for video, typically in the domain of analog, and I still believe analog has a big part to play. And this sort of leads into the idea, is it possible to look at ways of using analog and digital in a hybrid arrangement where it's neither one or the other, or a combination of both. And this sort of thinking came about with experiments that were done back in the early 2000s with Murray Greenman and Ken Hasselhoff with his work in narrowband TV on 80 meters. And a lot of stuff I learnt from those two gentlemen that has been very, very helpful. And Con, I must admit, ZL2AFP has also been very helpful on this current project, giving me pointers how the best way to approach doing such a thing. Well, we first got to start with the man himself, Mr. John Logie Baird. He started doing a lot of this work way back in the 1920s, a man well ahead of his time and what he could achieve within a few kilohertz with an AM broadcast transmitters. The resolution was not that good, but the key part of his system was you had movement, and your brain is quite clever to fill in the missing gaps with the movement. So if you have a rapid change of frames and low resolution, your brain tends to look at that image and tends to rebuild what is missing. So I'm working on the same concept where you look at what you can send and what your brain can interpolate and build upon within the image. And of course, with digital, there are a lot of compression techniques that are used. Some of those compression techniques can be used in the analog domain, some cannot, which I'll get onto later on. And this is also a good point to let everyone know that the centenary of narrowband TV or television in general is coming up shortly, probably in another 2 or 3 years. So it'll be an interesting time for ATV and how we're going to look at the work that was done 100 years ago and the work we're doing today, both in the analog domain and the digital domain. So you can see the man himself. I believe he was a Scotsman and coming up some very clever techniques with his scanning disc. Well, we'll start right at the very beginning, back in 2000. With work with 80 meters and transmitting television pictures via the 80 meter band. And this is what Con, ZL2AFP, had come up with his GUI. And it's very similar to what I've done in Linux. His one was written under PowerBasic, I believe at the time, for Windows XP. It did the job well. It's the same principle. It just simply scans the pixels on the desktop. So you open up a viewer, maybe VLC, or you open up a viewer within the application itself. Then you capture the information and you just do, in the case of Con's narrowband TV, for his high resolution mode, it took about 3 seconds or more to send a single frame. So you would see on the left is what was encoded. On the right, you'll see what's coming back at the other end. And you'll see in the image, you see the Luma component, and then the black bar at the on the right is your chrominance information. And you have that fine tune, which you get those pilot carriers. There's a pilot carrier within the multiple carriers, similar to what DRM uses, where you lock onto that pilot carrier to lock in the frequency and for all the other carriers with demodulation. Very similar approach that I'm using with the work I'm doing on the new narrowband TV mode. So what happens, what you see in the box there is basically what you'd see a slow scan. Whatever the beauty about going to an analog system is no matter what, you'll get a picture. And it comes down to how much noise can you tolerate before it's no longer a watchable picture. And of course, Con used some very interesting techniques, which I'm also using, where he does frame averaging, and he does some very other clever things with pixel averaging, which I also do, to minimize the noise, and you can adjust that ratio to get a reasonable picture. So you can see what was capable on 80 meters. This was all done within an SSB channel. And I think the work that Con did was amazing for the bandwidth used. But even at that time, I was very disappointed that we couldn't get moving pictures. And there was basically limitations in the equipment we're using at the time that pretty well restricted us to an SSB channel. I did some experiments also later on going up to 20 kilohertz with some other modes on 80 meters, and it made a huge difference to the amount of information that could be sent. But of course, you got other issues with the path. But the key part of his system was that you would transmit a sequence of images and you would store them as separate frames, like JPEG frames or bitmaps, typically bitmaps, at the other end. Then you'll wait, the transmission will go for half an hour. One of my transmissions across 80 meters went for about 45 minutes, transmitting a Looney Tunes cartoon. I think it was Sylvester and Tweety Bird. It was very short, it was about a couple of minutes. I transmitted that solid. My 80 meter transmitter got very hot solidly for 45 minutes. Then shortly after that, I ran the snippet of the sound through SSB. So I transmitted the frames one by one sequentially. It took 45 minutes to get a couple of minutes or so of frames. We saved them all, then we stitched them all together through FFmpeg, synced up the audio, and we got a TV picture through on 80 meters. So a lot of the stuff that came through on 80 meters worked that way, would catch the frames one in sequence. The only difference between what Con was doing and SSTV was this would transmit a long sequence of frames, and each frame you would store and you would rebuild them into a sequence of moving video at a later date. And typically you would stitch them together at, say, 1 frame per second or so, because that just minimized the transmission time that you needed to get through. So it was jerky, but you could see very jerky movement. It wasn't that good, but that was the limits of what could be done back in the 2000s. And I know Con was spending a lot of his time working on the software, trying to work out new compression ideas and ways to do things with his technology. And the next thing we need to go into is the difficulty of actually sending anything via HF and narrowband TV. It sort of seems to be an issue where phase and amplitude distortion are very common. We were running into this in a big way with, we worked into a big way with this with 80 meters, because 80 meters uses with NVIS, near vertical incidence, where the signal will go vertically up, vertically down. And of course, on that path, you would end up with a lot of phase amplitude distortion. With Con's narrowband TV, he would run a large number of FM carriers, spaced a few hertz apart, carrying the video information. And the FM provided a very high level of immunity, similar to what you get with standard SSTV with using FM carriers. Now, FM carriers are an extremely good way of sending video over on HF paths. So the multipathing was there, but it was to a lot lesser extent than what it would have been on the amplitude of the wave. And one experiment we did try, where we were trying to send amplitude information and phase information, it was a complete dismal failure. Mainly because we had a lot of amplitude distortion and noise coming in. But once we did everything in the FM, or the frequency/phase domain, the pictures came through relatively immune to noise. And of course, the distortion between what was sent and what's been received going through the ionosphere was always a difficult one to work with. Basically, when we tried to do work with digital, Murray was doing work at the time with Domino EX, and he was running error correction and some various modes he was playing with in the forerunner to what we have with Domino EX. He was playing with some modes before that were digital, running error correction. He was actually running error correction as part of Domino EX, and he found the same thing, is once you started putting error correction in there, you didn't really get a huge advantage. The advantage came from sending stuff very slowly, and having the noise immunity and a lot of averaging gave us an advantage. But you can see if you go straight up and straight down, you're going to get a large amount of phase and amplitude distortion, which is going to make it very difficult for a receiver to recover a signal. The experiments are done on 80 meters with DRM with Murray meant that we had to go down to something like mode D. This was the full broadcast mode of DRM to get anything through, and the reason it worked, it was locking onto the pilot carriers and trying to rebuild the phase information on the signals. So we had to go to those sort of links to get with the digital, but the analog could withstand a reasonable amount of distortion within the path and still present a watchable picture. So the analog had an extreme advantage over adverse conditions that you get on HF. And if you go lower to the horizon and you're within the maximum usable frequency, say you've got a band opening on 10 meters, and of course the 10 meter band's got plenty of space to do a lot of interesting experiments on, the phase amplitude distortion, because the angle going through the ionosphere is a lower angle, will be a lot less distortion that has to be corrected in the receiver end. And this gives you some background of why it's taken me so long to think up of a way of actually getting moving pictures transmitted over HF. Because you've got to take into account how the ionosphere is going to literally garble that signal coming back with the phase amplitude components. And therefore, you need a mechanism to minimize those phase distortions and basically make the ionosphere look transparent to the signal. So any ionospheric distortions that come through, the demodulator can counteract them. And one of the technologies I am working on to do this is called the Advanced Phase Detector, which I've experimented with AM radio for working out the position of the transmitter with respect to the receiver distance information. And I'm also looking at the feasibility of that design of an integrated signal processor for the narrowband TV, where you'll have a APC, which is an automatic phase control, as well as an AGC, automatic gain control, all integrated into the signal processor as part of the demodulator, to help correct any phase distortions / amplitude distortions coming through, with the ability to lock onto the phase of each of the carriers to have some sort of phase correction. And I'm also looking at the feasibility of using this technology possibly in radar, for example, where if you're looking at objects coming over the horizon, you're going to have the same issues with all the phase distortion and amplitude distortion and the various scatter effects you're going to have with ionosphere. So I'll be looking at the technology in that realm as well. But I think it could have a part to play to minimize the distortions that the receiver ends up receiving. We'll move down. And I'm not sure how well this is going to come through. But this gives you an idea of what we were receiving on 80 meters. Now, the frame rate we're running here is approximately 1 frame per second, but this is sped up. So we take the information, as I said, we store the individual bitmaps. They're not very high, so they don't take up a lot of space. And then what we do is we use something like FFmpeg, stitch all the frames together. And if the audio was transmitted later as SSB, we would combine them. In this case, there was no audio. Con didn't have any audio. This was live from the camera, from his webcam. And we sped it up. And that's what I would expect the new mode to look like. It's just going to be noisy. But you'll see movement, real-time movement. And there's a lot of averaging going on. So you can control the amount of averaging. It'll drop the resolution, but it'll also minimize the amount of noise. So you can sort of look at ways to mitigate the signal, the noise coming back through in the signal. So that is a key part.
At this point,
Over
sorry,
on the
Grant,
left,
to interrupt you, but
yep.
I think we should explain to everybody at home as well. You're doing this under challenging conditions because you only have a DSL connection. because you're going to be in quite a remote part of Canada. And what we don't want to lose is any of the actual video, the content. So you sent us the 2 videos that you're going to show ahead, didn't you? And maybe at the moment, if we can play that out, I think it will be a fair representation of what they are to show people it live from our studio rather than through your DSL, because it might have slowed things down a bit more. Is that okay?
Okay, I'll let you run the video from Con on 80 meters.
That's it. Now, we only saw a little bit of that actually in the transmission from you.
Okay.
So we're now back to you and your live slides, but and the next time we'll play a video as well. We have sympathised with having just a DSL connection as well.
Well, I think it ties in very well to this talk and what the motivation is to get back into ATV, because I'm in the middle of nowhere and we've got to get TV pictures to somewhere where people want to do ATV, to my remote location. So it means I have to think outside the box and come up with new ways of doing ATV. So I think it ties in well. Anyway, you'll see there that what happened is the noise that was received through the 80-meter path just was simply displayed as noise on the video. Now, these were FM carriers. They had a certain amount of phase and noise immunity, but ever so often with selective fading that happens with near vertical incidents, whole chunks or lines will literally disappear in the picture. But if you lose a line, you can still see there's an image there behind it. And with the movement, it just makes it a lot easier to see what's in there. And of course, if you get a whole sequence of frames and you have a frame buffer, which I'm working on with the newer software, you can do some averaging between those frames and just average out some of the noise. So these are the techniques that Con was pioneering back in 2000. Nothing new in them, but the way he was using them was quite clever. Now, on the left there, you see that there is a illustration of the pilot carriers and the information carriers. These are all FM carriers, and there looks like there was 72 of them from just looking at the table. I cannot remember, it's a while ago, but they all fitted within 2.6 kilohertz. And the importance of those pilot carriers, which is also important what I'm doing, is you need a reference, a phase amplitude reference, more of the case here, a phase reference to lock onto, so you make sure you're dead center on the information that's been centered, so you're not off to one side or back again. So once you've got the lock and you're actually locked in onto those carriers, you actually start generating a picture. If there's a mismatch between them, of course, the best way to describe it is what you get with FM television. You get a lot of black sparklies, you get a clipping on one that goes all whitish on the other, and it just makes the noise, just amplifies the effect of the noise. So you want to be centered. So these pilot carriers that are right at the edge of the pass band are fitted in there because they don't carry anything other than a reference to tune into the center frequencies of each of the carriers. So each one, so in Con's case, he's doing something slightly different to what I am. He would actually divide the picture up into 2 parts, the chrominance and the luminance part, and they'll all be transmitted as frequency, as frequency division multiplexing, where they'll all be on different frequencies. So the chrominance and the luminance would be transmitted together. I did have a long discussion with him on this, and he says the reason he did it is simple. It's easier. And he's right. It is easier to send everything at once. But in my case, I needed to think, okay, if I sent everything at once, there's going to be a lot more spectrum requirements. If I can sort of shift things to different times into the time domain, there are some advantages in doing that. And I spoke to Con about it, and he saw the merits of what I was planning to do. But he did highlight it's going to be a lot harder to do because you've got to synchronize. The data frame, so you're right at the beginning of the frame, so you know in the time domain which parts are the luma components, which parts are the chrominance parts, which parts are the wavelets, and the other part are the motion frame. So you've got to know where they are in the time domain, and therefore when signals get weak, you have to have the ability to accurately trigger at those right timing intervals to recover that information. Okay, we'll move down. I think that's a good illustration of what was achievable back in the 2000s. Okay, there's another video here. I'm not sure what you want to do there, David.
Yeah, I think we'll play this one out. So in the bottom right there, we're just seeing it, only catching the odd still frame. So I think just to be representative again of what you originally shot, we're going to now play that out.
To really get it together with some detail if things. nice and stable. It has a crystal oscillator for the tone decoding at 3579 MHz standard USA colour frequency. And it lets you get really good decoding. You really don't need any setting up for the frequencies. Just a crystal oscillator and everything works out fine. So it's a very good one for that. Ident and call sign from the mics that are on ABS, so that'll be quite good. Victoria and Wellington, holding Ricky's Quaggy, looking at the Belmont ATV repeater on the monitor.
Victoria, holding up.
And Ricky, Citadel 2 RW.
I think, okay, just looking at the video there, you can see that that video was originally recorded on 8mm. That was then copied to 8mm tape, I cannot remember, standard 8. Then that was recorded to VHS, and from VHS, as you can see the smeary image, that was digitized to an MPEG, I think initially an MPEG 1, then I took the original VHS and coded it to MPEG 2. And there's a lot of losses in the way, and the reason I decided to start with a VHF reference is I wanted to know, I had several recordings that were done on standard VHS. I wanted to compare the narrowband TV resolution to get some idea, to get something. I think VHS is a good reference point to aim for. It was not very high res, but you could see what was happening, and I wanted to work out what would be the number of carriers I would need, what would be the frame rate to actually get some movement. So I needed a reference. So that video was actually recorded as a loopback test through the Narrowband TV application and then stitched together with FFmpeg with the WAV file, and then that built up that video. So what you saw was compressed. The luminance was compressed. There was the only thing that wasn't compressed. Sorry, the chrominance was compressed. The luminance had very little compression. There was a lot of compression in the wavelets. That's the highest point of compression, and there was a little bit of motion compression in there. But when I recorded that was before I did a lot more work with the motion side of the frames. So at the moment, I'm running with a little bit higher compression. So what I ended up with through these experiments was a picture size approximately 240 by 192. Now, I couldn't transmit that over on HF. When I did the calculations, we're getting up into some horrific bandwidths. So I decided, okay, well, we can't run 25 frames a second. We can't run it at that resolution. So I decided to drop it down to 12.5 frames. And what you saw was recorded at 12.5 frames. It was a bit jerky when there's a lot of movement, but 12.5 frames seems to work. It's not brilliant, but it gives you the impression there is movement there. So the luminance and chrominance compression, I'm still experimenting with different compression ratios for the chrominance, but it's 4:1, and we're running basically odd and even lines in 2 different time slots for the luminance. And I discovered pretty quickly playing around with this technology that the luma part of the signal is very unforgiving. You cannot do any compression realistically with luminance in the analog domain, because as soon as you do any type of compression, I was doing some interpolation between the odd and even lines for the interlacing, and where I had one interlace running a lower resolution than the other, and I found that didn't work, because as soon as you do anything to minimize the amount of information being sent within the luminance channel, it just looks a lot duller, and a lot of the detail quickly disappears. So the luminance channel is very, very unforgiving, and I think a lot of people before me have run into the same problem. Con ran into the same difficulty, But of course, chrominance luminance pull down is definitely a good way of getting compression, and VHS had quite a horrendous pull down ratio for the luma channel versus the chroma channel. So you can get away with a lot of chrominance compression, which is an area where I'm going to have different modes where you can run at different compression ratios. Sure, the color is going to get smearier, get very smeary and horrible looking as you actually reduce the amount of color information or switch it off altogether to go to just straight luminance. The other issue I ran into is I had to go back to a base resolution. And the base resolution of 120 by 96, 120 pixels across by 96 lines down. And I found I could transmit that within, when I did the calculations and the modeling, I could get that down probably within a few hundred kilohertz. And with some compression, you could get that down a lot further. So I spoke to Con, and I say, look, Con, I'm having problems here. I'm having issues trying to get... I tried to explain the issues I'm running into with the chrominance and the luminance compression, and I spoke to him about some experiments he was doing with wavelets. And so I wanted a method of sending the velocity, the rate of change between pixels. Instead of sending all the pixels, I just wanted to send the rate of change between pixels, which was the wavelet component. So we had a bit of a discussion with wavelets. And I'm not sure if the mouse shows up, but here you can see this illustration. On the left is the raw image coming in. I picked this image because it's a colorful image with a woman in a clothing store, lots of bright colors, lots of detail. You got the discs in the background that have a very fine gradient in it for bandwidth, and the very fine dots. And what happens is I take that signal, I break it up into chroma luma, and that ends up in the box in the middle. This is the test application, and it would take the luminance, chrominance, build it up. That gives you a resolution of 120 by 196. Then I did another process where I stripped off all the high frequency components from the luma channel only, and they were sent as one bit of information that was sent as wavelets. Now wavelets just is simply on-off state. And that allowed me to send the velocity or the rate of change between the pixels, allowing me under very good conditions, if there's not much noise present, the wavelets would actually rebuild the detail lost from the luminance side, and you would actually get back to the original resolution of 240 by 192. And the beauty about using wavelet compression, one bit, is it took up very little bandwidth to get a massive improvement in the high frequency components. So I wrote this little bit of software just to do this and break the signal up into its various components, and that's what you see there. Then, of course, you can only go so far with software and compression. Now, this being a hybrid system, being digital, everything happening in the digital domain, some of the signal being sent as digital, some of it sent as analog, there's absolutely no room for bandwidth for error correction. There's zero error correction everywhere. If there's errors, you've got to encode the video and the audio and all the various parts that get transmitted in such a way that it's fuzzy. So if there's a bit flip or a bit somewhere flipping, it's not going to cause an error. It's just going to change a different, say, in luminance. It's going to be a little bit brighter, a little bit darker. It's going to look like fuzzy noise you used to get with analog television. So the idea, whatever's received just passes through the chain. If the signal from the AGC gets to a certain point where the signal is very weak, it'll just switches off the wavelet, then it starts doing a bit of averaging on the signal. So I had to look at how information is transmitted. Now, digital is extremely lossy when you take into effect that you have to have points in a constellation to transmit digital. And you have to have sufficiently low enough phase distortion and amplitude distortion to work those quadrants out where the information lies and what each one of those dots represents. So the whole idea of going to, say, 16 APSK or QAM or 16 QAM, 256 QAM is great. The more information you put into it, like 256 QAM, the more information you can transmit, but more error correction needs to be transmitted within the presence of noise. So the whole idea is, look, let's forget about this constellation stuff. We don't need it. Let's just run things purely as straight QAM. So I'm running 65,000 QAM, basically 8 bits squared. It's a word, 16 bits, so 65,000 states. So we can just call it QAM. And so therefore you get a round fuzzy blob. Well, we've got a problem there because we've got to control the amount of amplitude shift and phase shift to work within the confinements of the amplifier. An amplifier has its compression point, 1 dB, 2 dB compression point, so you can't push your QAM constellation into the compression point because it's going to add distortion. So I decided straight away we go to a spherical type of modulation where there are no points. Like if you've got 64 QAM, you get a square block. Those edge corners are basically lost because they run as the compression point of the amplifier. So I go to a circle. So I concentrate everything into a circle. And the noise reduction, what it does, since there's no error correction, it works out the probability of that being signal or that random noise. And there's several techniques I use to work out the difference between noise and the noise and the actual signal using good old noise reduction techniques. And Ray Dobie was a very good pioneer in this area with Dobie noise reduction, which we're all aware of. So a lot of his research was quite useful, and a lot of other research on noise reduction subsequently has been quite useful. So what you end up with is a QAM donut shape, because the noise will always appear right at the lowest point. So you've got two limiting factors, is the compression point of the amplifier and the noise at the receiver. So you want to concentrate the information where you have the least amount of distortion and the least amount of noise. So the modulation technique I'm using is this QAM NR system, where it gets rid of all the issues with the constellations, but the downside is there is no error correction. It's more akin to analog, but it's sending basically digital information that can be decoded. But the idea is encoded in such a way that a small error does not require error correction. It's only going to give a small error at the other end. Now, working through this, we have the graphical user interface. Now, I'm not a programmer, I'm a hardware guy. I like to work with soldering on and physical components. So learning software has been quite a steep learning curve for me, but basic. So I've done a lot with Gambas and Visual Basic. I did some background in that, and I found Gambas was easy to learn from my Visual Basic background. So what I did is I took what Con did. I had a encoder, decoder, and what I do is I have a media player, so I'm just running the media player that's part of the Gambas module. I am capturing the pixels from the display in the resolution of 240 by 192. Then I'm running through the various from that point. So as you can see, there are ability to take a file, read the file, encode it, transmit it. There's ability to go straight from a UDP stream. So you want to stream to the application, you can do it for a UDP stream. So you put the URL in there, you can do it from a webcam. And I'm also doing a lot with the good old PVR 350 because I'm still very much in the world of analog and composite video. And I can just feed a composite video signal straight into the back and get the PVR 350 to digitize that video and just display it, so I can just feed an analog video source into the encoder. Very useful. And of course on the other end you have the decoder. That's what the decoder looks like. Usual controls, contrast, brightness and all the rest of it. It has a few extra features, aspect ratio, because the problem these days we're 4:3 and 16:9, so it runs both. You just select which one you want to use. It has wavelet on off, so you can switch the wavelets off if it just gets too noisy. And it also has scaling, where you can adjust the scaling, because if it's really noisy you want to scale down the image, otherwise it just gets really distracting for the noise. So the idea is to just keep a picture present no matter what. Where digital has a cliff effect, it literally falls over. This will just keep on going, similar to what Con was doing back in the 2000s. And the engine behind this is FFmpeg. You hit record. The record simply captures the sound as a WAV file, captures all the images as bitmaps, and just goes bitmap 1, bitmap 2, bitmap 3. I've set a limit to 4,000 bitmaps, and hard drive space and RAM space are nothing these days, so 4,000 bitmaps is not going to take up a lot of RAM space on the RAM drive, so you just capture all those. Then you hit the record button, then it just runs a script in the background, tells FFmpeg to stitch all those frames together and then to stitch the audio in, and it spits out an MPEG-2 file, which I can then push back out the PVR350 MPEG-2 card as analog video, or I could just display it through HDMI. It's not a big deal. So I needed to have some way of testing the ideas and the concepts I was working with, so this is how I did it. This is the block diagram. I don't know how many people have got the CAT23 article, but it's published in there. There's a lot going on inside the software. First of all, you've got to, as I said, take the image, the raw image, break it into its parts, the luminance, the chrominance, the wavelets, and the motion. Then stitching it together in the time domain, very similar to how BMAC used to work in DMAC, the old analog systems. So you have a frame. It's made up of luminance, chrominance, wavelet, motion. Then you have two frames, and when two frames are received at the receiver, it interpolates the missing frame in between from the motion vectors and then gives you a frame to incorporate. So it allows me to, in theory, which I'm still perfecting, the ability to run at 6.25 frames per second, and it will interpolate at 12.5 in the receiver, again reducing bandwidth. But again, with bandwidth, it's a law of diminishing returns. It's like a bell curve. You get to a certain point with noise reduction and compression, and the compression used has got to be fully reversible compression in the presence of noise, because there's no error correction. So you end up with a bell curve. And the Shannon bandwidth rule is very real. I sent some very let's say, not very pleasant words have been used with Mr. Shannon. It is real, and the Shannon bandwidth limitations, I'm always cursing because it's there, and you've got to work within it, and the laws of physics are unforgiving no matter who you are. You've got to deal with it. So there's a limit to how much compression you can run within a given bandwidth, to how much resolution and how much video information you can send, and so it all comes back to how well you can process the signal to be immune to noise coming back the other end. The audio I've not spoken much about. It's basically the CQAM, which is what's used for AM stereo. I'm also looking at the CQAM system, and I'm also looking at the CAN system. The CAN system is very clever that it uses sidebands to send information, where the CQAM system uses QAM to send the information. And the idea, of course, is the amplitude carries more information than the phase. So you sum the information for the amplitude domain, you subtract the information for the phase domain, and that's how you send the QAM signals. And that applies for the video carriers and the sound carrier, where you just compress them down that way, and then of course you get you get left minus right, left plus right, and then you'd have line 1 minus line 2, line 1 plus line 2, and you get the idea of the encoding process. So it's a lot going on, and of course there are two noise reduction stages, one in the digital domain and another one in the analog domain, which I'm still working on. And I hate to say it, but with this project, it's been more frustration and failures than anything else. But as I've always said, with failure comes insight, from insight comes discovery. So I've got a good idea what doesn't work now. So it just leaves what probably could work. So we'll move down. A quick overview of the Win PVR350 card, MPEG-2 based. Oh, this card is amazing. With Linux, because the software and everything runs under Linux, you can talk to this as a file. You can say stream to this location in the kernel, which is dev drive for videos, blah, blah, blah. Stream the file from FFmpeg, and the way you go is so you end up streaming straight out of the card and into a TV monitor, and you can see down here on the Sony monitors the image coming back through the card. And it's very easy in software to enable the PVR350 to take analog video in, analog video out. And I can use HDMI, or I could use streaming, as I said earlier, with UDP, or playback a file. It's all good. So there's the hardware. They're not very common these days, but you can pick them up on eBay, next to nothing. And I believe you can get a PCIe to PCI interface connector, and you can plug them in, and you just plug them in Linux kernel, sees them right away. And I just find this a very useful analog to digital interface to work with anything I do with DATV/ATV. And the other part I have not gone into yet, because I've been focusing solely on the compression side, the noise reduction side, is the modulator, demodulator, and how I'm going to take the data out from the application into, say, the FPGA, which I'm going to then run the DSP modules to do the filtering and generate the carriers and all that sort of carry on. So I've been experimenting with this particular USB parallel interface module. It looks like it will have sufficient bandwidth to talk to an FPGA, and I can talk to that. The FPGA will talk to the various peripherals that I need, like the A to Ds, D to As, the static RAM, all the important stuff, to send the stuff out and generate the carriers. Again, I'm not a big software guy, so working with DSP, FPGAs and development software is a steep learning curve, but I have modeled some ideas how the transmitter is going to be built, or the modulator. And of course, the most difficult part is the decoder. The decoder's got a lot more going into it with the phase detector and the signal processor. It's the first time I've actually needed to use a signal processor for television. Usually you have a demodulator, then that feeds out the video signal. But no, you've got to have a signal processor to work out the probability of noise versus the probability of signal, and to do some phase amplitude compressions for any ionospheric effects, because this is a ionospheric mode that needs to counteract all those issues that you inevitably will run into. So that's what I'm tinkering with. At the moment, I'm taking a bit of a break from it. I'm just doing software modeling at the moment. I've got a few ideas drafted about the hardware design for the modulator, demodulator. Unfortunately, I just can't get something off the shelf to do it and budget. This has to be optimized to get the best signal-to-noise performance possible, and to encode the signal the best way possible to get the signal to be transmitted with the minimum within the presence of noise. Here is a basic mock-up of the idea of the transmitter. Again, that was published in CAT23. As it says, very much a work in progress. This has changed several times over, but the basic concept's the same. Everything comes into the FPGA. The FPGA generates all the timing signals through the PLLs and so forth. Takes the frames coming in from the software, stores them, alternates the frames, transmits them, encodes them. Then we get to the digital part where it goes from digital to analog, D to A. Then we have another section which is the analog noise reduction section, because once we get to the analog domain we run for another pile of noise reduction, which is basically good old frequency amplitude compression. And then that gets up converted up onto the 10 meter band, and then it can be just standardly amplified for a conventional amplifier. So, but this is the part that's going to be doing all the work, and it's going to take a lot of time. So I've already resigned to this being a multi-year project. It's taken me a year to get some idea on how the software is going to encode the signal and what needs to go into the software encoding to what goes into the FPGA hardware encoding side of it. So I've got that pretty well worked out at this point in time, but at the moment everything's pretty well got sorted on the encoder. Next year I'll be focusing on developing the hardware to maximize the signal to noise for transmission and reception. And that's pretty much a run through, and I'm pretty sure there are questions. So how are we doing for time, David?
We're fine. We have a good 10-15 minutes. As you're the last speaker of the day, actually, it's fairly casual or relaxed, should we say. So if you at home have got lots of questions and comments to ask Grant, you can fire away. So please do that now. We haven't actually got anything yet, I think, specifically about this, but I'm sure everybody's been intrigued with your introduction. And as you mentioned...
Well, we can certainly go over it.
Yeah, absolutely. You did mention this, and this is a good point to mention, because some of the people watching may not be members of the BATC. And as part of your membership with many other things, you do get this wonderful magazine. And as you said, Grant, there's a big article in here, I think 4 pages, possibly 5, this month, all about what you just described, a new type of hybrid television. So particularly, I think if you don't just want to do the HD, in fact 6 pages looking at this, so lots of information there in the latest CQ-TV magazine. And there is a lot that you can do, your experiment yourself. You've been honest and said you're not a software engineer, which of course a lot of the people we've spoken to today and heard from today are software engineers. You're essentially hardware, and I guess you've been dragged along and had to learn some of the software for some of these techniques. It was a wonderful project.
I'm an old school broadcast engineer. I came into the world of television in the analog days, very familiar with an analog video signal. I've built multiple VSB transmitters, FM transmitters, filters, group delay correctors, you name it in the hardware domain, I've done it. But I've been dragged kicking and screaming a lot of the people into the software era, and I admit there are a lot of advantages into using software, and I've had to learn to work with software. Luckily, in the days of DOS, we had BASIC, Quick Basic, and I used to write applications in Quick Basic, and then went on to work with Visual Basic, and of course Gambas is brilliant. It's basic for Linux, it's Visual Basic for Linux, and it's just very easy to work with Gambas because you just pull in the various modules. You want a media player, pull in the media player module. If you want something else in there, you can put in other modules like encryption, compression algorithms. Because I initially thought, okay, I can use a run length encoder and that'll do the compression. You can't run a run length encoder and Hoffman encoding and all this fancy doodah stuff because you need error correction. Guess what? There is no error correction. So a lot of stuff you instinctively think you can work in the digital domain doesn't apply to what I'm doing with this hybrid mode because it doesn't use error correction. And that has been a total paradigm shift in thinking of sending information in the digital domain that's sort of a hybrid between analog and digital that has zero error correction, but only only has a bit of noise reduction to minimize the impact of noise on the valid signal you're trying to receive. And I'm still actively experimenting with ways to interpret in the signal processor and the receiver to differentiate between noise and the valid signal. Because no matter what, how noisy things get, you want a probability to know where that luminance value or that chrominance value lies and to build the picture. So there's a lot of processing involved there. And subsequently in the article, I've been looking at AI. In another 10 years, we could be looking at an AI module. We take the noisy TV picture into the AI module. The AI module has the intelligence to subtract the noise from the video. And I think that's going to be a very interesting development in years to come.
Yeah, and I guess that when you think about the analog world, analog electronics, that's always going to be the most efficient form of communication because you're not changing it in any way, are you? You're just transmitting it. It's only when you can't transmit it because you haven't got enough bandwidth, or maybe you're trying to get it over in a very, very noisy environment, that you need to encode it. So maybe your idea of combining really the two, some analog and some digital, might be quite a nice fresh approach.
Well, no one's done it. Obviously, someone has done it in the past and failed and gave up on it. But I'm a sucker for punishment, so I've decided I want to do ATV. And I live in the middle of nowhere, 350 kilometers north of Toronto. And what I've got to do is compress the video/audio information down to a point where I can get it over an HF channel. And there's only one band that will allow me to do that, be 29 megahertz. So I'm looking at ways of shoehorning it into that band. And maybe in another couple of years, maybe by the centennial of John Logie Baird, we'll have some pictures on the air and be able to enjoy the hobby once more.
Wonderful, yeah. I mean, would you say that as someone who's come from being essentially a hardware engineer and, as you, in your words, dragged kicking and streaming into the software era and things, would you say that this sort of project is a good way of trying to learn a bit about software if you are mainly a hardware engineer? Yes,
I think it's good because it has a balance of both. Instead of just bodging a bit of hardware, you buy, say, an Arduino and plug in a card, write the software. Sure, it's working at the hardware level, but in this application, I have to optimize the hardware to work for this particular mode, maximize its performance in these adverse conditions, and then apply software to get it all to work. So it's interesting because using all my hardware experiments and resources and what I've done in the past and how hardware goes together and what works and what doesn't work in that domain, then I'm looking at, in DSP, how would this work? Could I do this? So it is very interesting, and I'm finding it a very interesting area because I've never really delved into digital signal processing and your various forms of filters you got there, your averaging filters and various other ways of using wave tables to generate sine waves or triangle waves. And it's very interesting just learning DSP. So I find by taking on these projects are very challenging, but I learn volumes from doing them, put it that way.
Absolutely. Okay, well, we have one question so far, and I'll read that to you. But if you've got a question or comment, or if you've ever done anything with narrow bandwidth television like this, or also if you could help, and if you're interested in joining Grant on this project, then please put a note into BATC messaging or YouTube chat right now. Now the question we've got is from Dave G8GKQ, and he asks, what FPGA development environment is Grant going to use?
I do everything with Qwertys because I've tried Xilinx. I just don't like Xilinx. I'm a hardware guy. The good thing about Qwertys and the Intel chips is that you can go to the symbiotic level, and if you want an OR gate, you cut and paste, put an OR gate in there. So I like visualizing the logic sequences, the OR gates, the AND gates, and that. And I like that at the top level, and then I'm learning VHDL. VHDL is a bit like BASIC, but a bit different. But with VHDL, I can program a module that's specific. Then I can bring that module and import it into the schematic layer at the top, and that helps me to think, okay, here's the hardware part, here's the software part, and it makes the development from my background in hardware a lot easier to do, because software guys will jump straight into doing VHDL and that's it. And I've had to work with those people, and it does my head in, because I'm a visual person. I've got to see a schematic, how the thing lays together, and how this VHDL module fits into the overall structure. I think that probably gives you a good answer of the way I've approached it.
Yeah, absolutely. Well, I must admit that's the way I tend to think as well. I was never much good at the theoretical things at school, but give me a circuit diagram or an actual PCB to hold, and I get it. So this does seem a great project to get involved with that. We've just put your website, or actually the QSL, because you go on your website, it's ZL1WTT. I've got qsl.net/ZL1WTT, and I think that links you to your old New Zealand website. Is that right?
Yes, I think I put an explanation on there. I just, of course, new call sign, I have to go back to QSL and say, hey, this is my new call sign, and I'll have to go through re-updating it all. So on the title page there, as you come into it, does talk a bit about it's now VE3 X-Ray Tangle Victor. And I must admit, I have been very lazy of late with work commitments and other things. I haven't really done any updates. I think the last updates I did on the website were back when we had lockdown, and I had the time. So I haven't really updated much on that site, probably in the last 2 years, so it's a bit antiquated, but it's there.
That's all right. And you would encourage some people, if they're keen. You worked with Con, you said some years ago, and if there's anybody who's keen to work with you on this, it sounded from when we talked the other night at rehearsal that you would be keen to work with them.
Well, I'm quite happy to I think it's a good idea to get a broad perspective of ideas, because right now at the moment I've hit the wall. I've had failure after failure after failure, and it's good to just take time out from the project, and I probably will get back into it in the spring. But maybe someone will come along with another idea that may push things along again. But I'm just working on other projects unrelated to Narrowband TV. I'm still playing around with the demodulator idea for, as I said, some other applications. And that's where I'm focusing. Sometimes what I do is when I hit a brick wall in a project like this, I go away and do something totally different, maybe for 2 or 3 months, 6 months. Then suddenly I get an epiphany or an idea. Maybe that will work. Then I come back to the older project, and that's how I approach development of ham radio projects in general and commercial projects. To avoid burnout, it's important that you sort of go far as you can. It's got to be enjoyable. Once the enjoyment goes, you just switch projects, go on to something else. Then, okay, what if I did this? Then you start thinking about these older projects, and you come back around full circle back on them again. And that's how I approach taking on projects like this. I never go 100% for 2 or 3 years and develop it. It's usually 3 or 4 months here, maybe another 2 or 3 months next year. Then when I discover and my skill set improves a bit more, I'll try something else, and I get another breakthrough. So this is why it takes so long for any of my projects to see the light of day now, because it's just a steep learning curve. And I just need, for my own sanity, to take regular breaks and do other things. Makes
sense. A good, healthy lifestyle to do that as well. A couple of actually comments for you. Dave M5TXJ says, is this another option for 10 metres perhaps? And then Mike G0MJW says, top band would be much more stable. So obviously with such a low bandwidth, you could probably work on those bands. Have you thought of that yet?
We'll start with 10 metres. Well, basically anything above 10 megahertz has got sufficient space to run this, but 29 megs is ideal, because when I tune around on 29 megs on the band opening, you have the guys running AM around 29 megs. Then you've got the guys running FM on the FM repeaters up at the top end of the band, and generally there's very little in the middle there, and this would fit quite happily in that little space in the middle. On 10 metres, and I think it's the only realistic band, because this is designed to work with ionospheric propagation, And Con Murray, Z1 BPU, always found it amusing when people would transmit Domino EX on 2 meters for an FM transceiver. And he said, well, that completely negates our entire purpose, because you're taking a frequency hopping MFSK signal, then you're frequency modulating it, then you're transmitting it, demodulating it back to FSK, then decoding it again. So you go through 2 steps, and you completely negated the whole purpose of the modulation system. So one thing I did learn from Murray is that the modulation system and the way the modulation works is pretty well dictated by the mechanism of propagation. So yes, it would work on higher frequencies, but the advantages would not be there, because the advantages are there in the amplitude phase compression that you need to do to rebuild the signal from ionospheric distortions. Of course, it would transmit on higher bands, but it would not be optimized for higher bands, because you wouldn't need to go to this same extreme lengths to do those corrections in the receiver or / the signal processor.
Yeah. Okay, we have got a couple more questions just come in, sneaked in at the end. Actually, a comment, I think I can understand it. Michael EA7KIR says it's just taken him 2 days to realise that an IR filter, I think that should be, is just a CR filter. So maybe that's someone from a software perspective just coming into the hardware world. Mike G0MJW says we did manage to send DATV over 10 metres using QPSK in 20 kilohertz. But the multipath was the issue. It worked once or twice for a few seconds. That was DVBS, and it doesn't really cope. He says that another approach might be to use coding like DRM. As always, the challenge is the DSP.
Yes, that's a good approach. Well, I've gone to a different approach. As I said, I'm using like a radar system has. You have a receiver, and that feeds to a signal processor to filter out all the noise and the unwanted information. I'm taking that approach here, where the demodulator and the signal processor are integrated. You have an APC, which is an automatic phase control, and an AGC, which is automatic gain control. It comes back from the phase detector, and then it talks to the FPGA. This is done with PWM. So it's all pretty well done in the analog domain. Then there's a control loop that comes back. Then yes, a DRM approach is a good approach, but again, it's very wasteful on bandwidth, because you have to send a huge amount of error correction for it to work. So the pilot tones and using the pilot tones to rebuild a characteristic of the ionosphere is a very good idea, and that's what I will be following in the signal processor. Is I'll be locking onto the 24 carriers, checking their phase amplitude from a phase amplitude reference, and from that putting a phase amplitude correction back into each one of those carriers at the receiver. So the signal processor is taking a lot of time, and this is why I've taken time out from the project. That is getting quite involved in rebuilding those phase amplitude corrections. As I said, this mode is designed to work no matter what. So you're just going to get a very noisy picture with, say, QPSK. Of course, it's very phase dependent, phase amplitude dependent. Once those phase errors start building up, the error correction can't cope and it falls over. This system doesn't have that. It does not use error correction. It only uses noise reduction.
Okay, thanks, Grant. And one final question, I think, for you from Charles G4GUO. Do you have symbol rate restrictions on HF in Canada like the Americans do?
It's not really applicable, because it's not really digital, it's hybrid. I don't know how symbol rate would apply in this case, because
So,
it's
as you say,
basically
it's more
a frame,
analog,
it's a
isn't it?
fixed frame,
Yeah.
and so it fits within, depends on the mode, depending on which bandwidth you use. So it's a difficult one to answer, because it's not a conventional modulation system.
Well, one thing is for sure, that this certainly fit as part of our licenses, I guess in all parts of the world. The key word, I think, is probably experimentation. It's to encourage people to experiment. And you're certainly a great example of someone who's taken your license and experimenting and thinking of a new way of doing something. Thank you ever so much for joining us today with a brilliant presentation on narrowband television.
Okay, well, thanks for your time.
Many, many thanks, Grant. And that almost concludes the British Amateur Television Club CAT23 online convention, and we hope you've enjoyed it. Now, it was about to finish it, but I actually had a question which I shouldn't ignore, because it was actually asked of us, Tammy and me here in the studio, and it was from Julian Baldwin, who says, David, at the end of the show, could you give us a brief rundown on the equipment and resources needed to produce the show? Well, we weren't prepared. We didn't have background cameras or anything, and our cameras are fixed in the right positions, as you can imagine, for this. But what we did do a few minutes ago is we took a picture, a still frame, which Tammy's going to put up now, and I can just talk you through it. So this is what I'm seeing. You're looking at behind me. And there's about, I think we're using 6 computers today. So on the far left is an extra computer, which we're using for some extra media playback that we needed to do for films and videos and inserts and things like that. The big iMac on the shelf there, that's being used for one of the streaming. That's streaming, I think, to YouTube. And the next, then on the ground there, you can just see an audio mixer, and then next to that a vision mixer, which is for those of you interested, because of course most of these productions that we do, people aren't really interested in it, but this is a Roland V8 HD, which is very good. There's on top of that is a monitor, preview monitor, showing all our different inputs and sources. Then behind my head on the left there is what we call our caption Mac. That's running basically a sort of slideshow. We use Keynote, we use Macs exclusively here, and we're using basically a Keynote to put all of the captions and graphics and things that we might need in that. Countdown timers and things were videos as well that Tammy made up with those, and we started them at appropriate times so that we didn't have hard times for presenters to finish, because that wouldn't really work. The Mac that you can't quite see because my face is in front of it is where we're monitoring the BATC feedback, and that's also showing us the comments that you're asking on BATC. To the right of that you can just see there was Grant's head there. That's the Zoom computer, which is linked to our guest contributors with that. Above that you can just see we only use a couple of small Panasonic semi-pro cameras, which are HD, but they're really very, very good. There's a sort of homemade autocue above that, which isn't really an autocue as such. It normally just puts notes and things like that up from a script. There's a little piece of paper I stuck there, if you look there, with the running order of today. That's just in case something goes badly wrong and I have to very quickly fill, so I could have talked it over. To the right of that, another computer, that iMac there, that is streaming out to BATC and is also making a hard copy recording of it. So I hope that's interested those. I've never done that before, talk it through. I will just add one little thing, not to say that we've done a good job, but if you think we have, one of the reasons, to be honest though, with all this, you can have all the equipment in the world, but if you don't do a bit of planning and preparation, and also we always insist on a technical rehearsal with all our presenters and guests. As you may know, we do a lot of these things now, both for our Norfolk Amateur Radio Club, which is what I'm chairman of and we're both members of, and also for the RSGB, and a lot of it just comes down to planning, and I think even the best professionals who've been doing it many, many years will agree with that. If you don't plan, then it doesn't really work. Even though the two of us are sitting next to each other, you need to know what's going to be happening. Hope that's provided a useful insight, and I'm sorry it's a long answer, but I hope it's enough. Maybe if you want us to do this again, what we could do is maybe put a little camera up in the ceiling or something and see a bird's eye view of it. That's just an idea, maybe for another year. But anyway, if this has been one of your first experiences of the British Amateur Television Club, then maybe you'd like to consider joining us, because membership starts at just £8 a year, which includes lots of benefits, including the magazines you saw earlier, weekly TV nets, events, and a very useful projects and parts shop. You can find full details about the club at www.batc.org.uk. So it's goodbye now from Vision Mixer Tammy M0TC, just off to my left, and myself. And after this short video, we'll go back to our chairman, Martin G4FKK, to formally close the convention. Bye-bye.
Well, thank you for that video there, and thank you to all the presenters for their time and effort, and for everyone for tuning in. I've got to ask David just now how many we've had. I think we had about 145 at one stage on the BAT streamer, but I'm not too sure how many we had.
It's about 145 to 2, and then about 45, 50 on YouTube.
Excellent. There you go. So that's good stuff. So I want to thank the speakers. Tim MW0RUD's finally got the timing settings on right through my thick skull. So I did work out the other day, Tim, how to change the colour from red to, well, I've got it as a rather unpleasant yellowy green, but I can see why you chose red. It's much better. And Mike G0MJW, Mike stepped in right at the last minute to fill a gap we had in the schedule. And Mike, that was absolutely brilliant. You've convinced me to fire up KiCad, KiCad, KiCad. That's the 3 versions of what it's called I've heard today. I'm going to move away from my old version of Eagle. That was very inspiring. And the 1.5mm 50 ohm track was useful too. Some encouraging news there regarding the Serret replacement from Dave, GKQ. Thanks for doing that, Dave. Looks like there's plenty of planning going on and plenty of opportunities too for some future amazing gadgets. And the unrehearsed link up with Gilwell Park Scout Centre there, absolutely astonishing. I didn't realise Frank was such a great presenter, and Lawrence did some sterling camera work there with an iPad, I believe. So we just want to make sure the BBC don't poach you, Frank. Frank's also the CQTV editor, so where on earth he gets the time from, I don't know. And Michael, DL5OCD, unravelled some of the mysteries of DATV, not so easy. I say mysteries because I have downloaded it and decided maybe I'll wait for the GUI. But now I've seen how you drive it, Michael, I think I'll give that another crack. And Grant, that was absolutely brilliant. I kind of think the work you've done is more like a doctoral thesis, really, but you managed to explain it so that my aforementioned thick skull absorbed it all. So that's very good. So I shall now formally close the BATC CAT23, but not before a special thanks to David and Tammy giving up their time to make CAT23 online so slick and professional. That's amazing stuff. Thank you both very much for that. And I'd also like to thank Mike MJW and Dave GKQ for the very long QSO they've had today on Oscar 100. So thanks again. David's going to put a slide up of where you can join the BATC, email the BATC, volunteer for the BATC, and etc. So thanks again. See you all at CAT24.